This is quarter one review sheet A, picking up with question number 12. Use calculus to write a convincing argument whether there is a zero somewhere between 3 and 5. Well, let's stop and come up with a plan first here. If we put 3 into our function, we will get negative 3. And if we put 5 into our function, we will get 5 over 1. So, does it cross 0 in between? IVT looks like it should work, but is there a continuous interval here from 3 to 5? We see that f of x has an infinite discontinuity at x equals 4. So let me, maybe as long as I've got this much, f has an infinite discontinuity at x equals 4. So IVT does not apply on the interval from 3 to 5. It would apply to any interval that doesn't contain 4. So remember that rational functions are continuous over their domains. Unfortunately, 4 is the only number that is not in the domain of this function. So we are finished with that argument. If you were tempted to answer this question using pre-calc, I suppose we should go back and consider that as an alternative. We know that we've got a vertical asymptote at x equals 4. The degrees are equal, so the horizontal asymptote is y equals 1. Put 0 in. We'll see that 0, 0 is an intercept. And we already know a couple other points here. At 3, we're at negative 3, and at 5, we are up at positive 5. So we know the only intercept, the only 0 of this function is at 0, 0. So choosing what we know with pre-calc, we could also come up with an argument that way, that there are no zeros between 3 and 5. All right. Sketch a graph with each of the types of discontinuities. So your answers will certainly vary. So we could have a removable discontinuity. I guess that's supposed to go in the blank. We could have the one we just did with the vertical asymptote. So this is an infinite discontinuity. And a jump discontinuity, probably our most common function. And it didn't say we had to give the equation, but you certainly think of this with a jump discontinuity. So you could give any types there as long as you have the 3 different types of discontinuity. For which of the graphs in 13 does the limit exist? Well, the limit does exist here. The little guy on the left and the little guy on the right get close enough to shake hands. So the limit exists only at a removable discontinuity. All right, the 3-part definition of continuity. Below each, sketch an illustration of a graph that fails that. Well, first, we want to say at x equals a, if f is defined at a, so we could maybe put this in the form of a question, or I don't know, doesn't matter. F must be defined at a. Or you could say f of a exists. So for example, we could have f of x equals the square root of x, and perhaps a is over here. Perhaps a is equal to -2. So it's not even in the domain. So it certainly isn't continuous there. The second requirement is that the limit as x approaches a of f of x exists. So that might not work if we had an asymptote or if we had a jump discontinuity. So we could use one of the functions that we've had before here. So if we had absolute value of x plus 1 over x plus 1, and here a would be equal to 1. So the limit doesn't exist, so it certainly can't be continuous there. And our third question then is, if the first two both work, then is the limit exactly what we would get by directly plugging a into the function? So is the whole plugged in? And we want an example here that doesn't work. So for example, a piecewise defined function that has a pop point. So let's say here a is equal to 3. So if we want an example of a piecewise defined function, so we could have anything here. X plus 1 if x is not equal to 3, and 4 if x is equal to 3. So there we would have a piecewise defined function, and you can make up any example. But a pop point would be the way that this might not work. So f of 3 would be equal to 4, and our limit here would be equal to whatever this value is, 3, 2, 3, 4. So in this case, 2 would not be equal to 4. Okay, oh, why did I say that? X plus 1 at 3. I guess I happened to choose exactly the wrong numbers. Go figure. All right, let's try that again. 3, 4, 3, 5. All right, so here the limit is 4, and it does not equal 5. Sorry about that. All right. And I guess that is the end of our worksheet. I thought there was another problem.